as well. So in this lecture, we are going to look at the linear programming formulation of a game theory. We started with linear programming problem and we are ending at the linear programming problem. So we have already seen in the context of game theory, we have already seen what is a situation when a pure strategy solution exists and under what conditions a mixed strategy solution exists. So why there is a need of third thing, that why we need to formulate it as a linear programming problem. So this is the first case. If saddle point exists for m cross n game, then nothing to do, because we already know in this case the maximum becomes equal to minimax and the question ends there only. So that gives us the pure strategy solution. And the second case is the saddle point does not exist for a m cross n game. Then we have the two possibilities. The first is, if the game is either 2 cross n or m cross 2, then we can use the graphical technique. So we have already talked enough about this graphical technique in the previous lecture, that this is applied on this kind of games, that either the number of rows of the matrix is exactly 2 or the number of the columns of the matrix is 2. That means, in other words, it means to say one of the player is having exactly two strategies and the other can have any number of strategies, obviously greater than 1. So in that case, we can use graphical technique. So we are left with this case. So what will happen if it is a m cross n game and both m and n are strictly greater than 2, then we have to do the LPP formulation. So in that case, we have to do the, just a moment, LPP formulation. So it's clear now when we are supposed to do the LPP formulation, saddle point does not exist, this case, and both m and n are strictly greater than 2. So now let's talk about how to formulate the linear programming formulation, because that's the only thing we need to learn, formulation. Because once a linear programming problem is formulated, we know already how to solve it using simplex or big M or two-phase method, whichever will be applicable. So we won't be spending time on the solution part. We'll be just learning the formulation part of the m cross n game. So there will be two LPPs associated with the two-person zero-sum game. So you know this meaning of this term, two-person zero-sum game. We have two players. So one LPP will be formulated for player A and one LPP will be formulated for player B, because we know that both of the players have opposite objectives. One of them is trying to maximize his minimum payoff and other is trying to minimize his maximum loss, you can say. So because the objectives of both the players are different, so their LPPs should be different. And essentially we will learn that it is sufficient to just formulate one of the LPPs. The other can be obtained from the same. So I'll talk about it later. So let's first look at the LPP formulation for player A. So if you remember, player A has m strategies, because if you're talking of m cross n game, then obviously m is the number of strategies of player A. So let their notation is A1, A2, AM. And we know that we always define the probabilities, that x1, x2, xm be the probabilities for A to choose the respective strategy, because we are in a case when pure strategy solution does not exist. So obviously in this case, the solution will be in terms of the probabilities. So we define m decision variables for x1, x2, xn, which are actually denoting the probability. Now you look at the matrix representation of the game in order to understand the LPP formulation. So although it's a 4 cross 5, but I have actually written it A1, A2, A3. Suppose this is a mth row, and on this side B1, B2, B3, B4. Instead of B5, I have written it Bn. Say this is the last column, just to give you an idea of a general m cross n game. So this is the payoff matrix which is given to us. So you just remember how we dealt with this situation in the previous lecture, when we were given the probabilities for these strategies of player A, x1, x2, x3 up to, this is kind of up to xm. So these are the probabilities. Now we know that when we know the probabilities, we can find the expected payoffs. So you remember how we were finding the payoffs for player A, that if B chooses strategy B1, what is the expected payoff of player A? A11 into x1 plus A21 into x2. In yesterday's example, because there were only two strategies of particular player A, so that's why it was just sum of these two terms, A11 into x1 plus A21 into x2, and that's why it was we were able to solve it graphically. But now the formula will be still same to compute the expected payoff, but since the number of variables is more, therefore we won't be able to solve this graphically. But the underlying theory remains the same. So you compute expected payoff of player A, A11 into x1, A21 into x2 plus A31 into x3 and so on, plus the last term will be AM1 into XM. So this is the expected payoff of player A if B chooses strategy B1. So it's the same thing I have written here. If B chooses B1, this is the expected payoff. So in summation form, I can write it like this. So it's 1, 1, x1, 2, 1, x2. So it's I1, xi, where I is running from 1 to m. But this is only for B1. Now you replicate the process for other columns also, that if B chooses B2, then what is the payoff? If B chooses B3, then what is the payoff? So you can write the general formula from here only. So you know if B chooses B2, the payoff is going to be A12 into x1, A22 into x2, A32 into x3, and AM2 plus AM2 into xm. So I can generalize this, that if B chooses strategy Bj, then this is the expected payoff. 1j x1, 2j x2, where j starts from 1 to n. So in summation form, this takes this as the general form. Summation is running over I because you are adding row wise aij into xi. So this is your expected payoff of player A if B chooses Bj, right? And then you remember at a particular time, what was happening in the graph, that one expected payoff was representing one line, then another expected payoff was giving you another line, and then the third expected payoff was giving you another line. And then you were finding the minimum of these payoffs. So this is a function of I, this is a function of xi, that you have to compute the minimums. And then out of those minimums, we were finding the maxima. So the same logic will continue here to formulate the LPP, that these are j values because j is having n values from 1 to n. So these are n values. So out of these n values, we will be computing the minimums, which will be a function of xi because xi is a variable, and then we will maximize it. So that gives you the objective of the player A, because we are thinking from the perspective of player A. Player A is trying to maximize his minimum expected payoff. So these are all payoffs. This is the same expression which I just computed. Summation I is equal to 1 to m aij xi. So you have to take the minimum, where minimum will be chosen from these n values, and then that will not be a fixed number because they all are functions of the decision variables xi. So that function you have to maximize, because this cannot be a number. There is no point in maximizing a number. This will be a function of the variable xi's, because aij's will have fixed values in the question 2, 3, -4, whatever it can be, but the variable xi's are going to retain. And we know that this condition is there, the sum of probabilities is equal to 1. So that's a default constraint, because now you see where we are heading towards. We are trying to just formulate the linear programming formulation, linear programming problem. So for that, we need constraints as well. So this is objective function, this is a constraint, and obviously these are probabilities. So actually, you can also write xi's are less than equals to 1, all xi's, but that need not be written, because since you have already written this x1 plus x2 plus xm equals to 1, and all of them are non-negative, so it obviously makes sense that if sum of some non-negative numbers is exactly equal to 1, so individually they cannot be greater than 1. None of them can be greater than 1. So that's understood. So no need to write it separately as a constraint. Even if you write that, that will be going to the category of redundant constraint. So you just need to write the non-negativity and this constraints. So this is sufficient to capture their bounds, that all of xi's lies from 0 to 1. So that's our programming formulation, because that's what we were doing in just deciding the strategy combination, deciding the xi. But if you look carefully, this is not a linear programming problem. Because if you remember, how does a linear programming problem looks like? In a linear programming problem, we have an objective function, maximize or minimize. Z is equal to, so here we should have a linear expression, and then subjected to whatever the constraints we write should also be linear. So constraint is okay, it's a linear function, there is no square term, there is no product term, and the non-negativity variables is also there. The only problem is with the objective function, which is not linear. If you remember, we had a similar question in tutorial sheet second, the very first question, where you were asked to linearize the given problem. So because in place of this expression, I just need to have a linear function. So maximizing the minima of something does not qualify in linear function. So that means I need to modify the objective function. So exactly same technique we will be following, which we had followed at that point. So this is not linear programming problem. So what we are going to do to convert this into LPP. So whatever is this in the bracket, I need a replacement for it in the terms of a linear function. So I'm just calling it another variable v. Why I'm calling it v? Sorry, why I'm calling it v, because ultimately you know that whatever is the value of objective function is going to come, that is going to represent the value of the game, because these are payoffs and you take minimas and then you choose the maxima of that. So whatever that final numerical value is going to come of the objective function, it's going to represent the value of the game, the final payoff of the player A. So that's why this notation is, we are defining it, denoting it by V. So this V is denoting this minimum of this. So this minima up to this point, we are just denoting it by other variable. And now I have to use this information since V is minimum of certain a set. This is a set having n values. So V is minimum of them. Obviously V is also going to be a function. Again, don't get confused that V is going to be a number because the variables xi's are there. So V is also going to be a function, a linear function. Just like this is the same thing, this is a lower envelope. This V is denoting this time the combination of linear lines, the lowermost envelope. So since V is minimum, so mathematically that means V should be less than equal to each one of them individually. So for all J, V should be less than equal to these these elements of the set. And since this can be rewritten like, I am shifting just this to this side because this is now giving me some constraints kind of structure. So we know how to write constraints. We shift the variables on one side and on the other side we just retain the constants. So that is why I'm shifting it to the other side and writing it, rewriting it like this. So actually this is the new set of constraints. And how many constraints are these? These are n constraints, as you can see, right? So that's it. I got these additional n constraints. This original old constraint is obviously there. This non-negativity is still there. So but I have got a better structure, which is actually the linear programming formulation. So maximize z equals to v, because whatever this was, we replaced it completely with whatever this was up to this point. We replaced completely with another variable v. So maximize z equals to v. So z is just notation for the objective function. Otherwise, don't think z is a variable. If you are familiar with this notation, we always denote the objective function with z. So z is coming from there. Subject to, so these are the additional constraints, n constraints. These will be n in number. I've written in a combined form, but if you will elaborate them, it will give you n constraints. And don't forget this constraint, default constraint, which is the sum of all xi's should be 1 and the non-negative. So that's it. This is the LPP formulation of player A. Yeah, one more thing here. What about the sign of V? Because our original decision variables were just xi's. See, aij's are not the variables. Aij's will be having fixed values, will be given to us in the question. So don't get confused. Our variables are just xi's. But V is also a newly defined variable, which is actually a function of xi. So we need to also define the sign restriction of V, whether V is positive, negative, or whatever it is. So V is actually unrestricted. Why V is unrestricted? So this is clear because although we have already done questions, we know that the value of game can be positive as well as value of game can be negative also, because in some cases A wins, in some cases B wins. We didn't do any example in our lecture where V can be negative, but in general it can be. You can see that in many of the questions. So you can see mathematically why V is unrestricted by looking at this, the way we define V. Let me go back to that definition of V. See, we defined V is this minimum of these numbers. So you know xi's are non-negative, but aij's can also be negative. Aij's can be negative also. The multiplication of negative into positive can give you some negative numbers. You see, yesterday when we were drawing the graphs, then some of the lines were going below the line, zero line. So they were having the negative values also. The payoffs were becoming negatives, right? So that's why this V, the value of game, can be negative as well, and it can be positive as well. That means it really depends upon aij's, what aij's will be given to us. That will change the sign accordingly of V. So as a variable, this comes in the category of unrestricted variable, because that's what the meaning of unrestricted variable is, that mathematically just by this much information I cannot fix the sign of it. In some problems it will be positive, in some problems it can be negative. So that's the LPP formulation complete of player A. And we will do example, and then you will realize that although we have written it, but you don't actually need to remember this. If you want to remember this directly, you can. Otherwise, directly we can formulate just by working on the example. Because the same technique which I have used here to reach at this formulation, the similar technique we will be using there in the question. But it is helpful that you remember that the sign of the constraints are less than equals to 0, V minus this, because that's the only thing which you need to remember. Otherwise, rest of the things are maximized at equals to V, and this constraint is the obvious constraint. So now this is just the LPP formulation of one player, but as I told you, we also need to formulate LPP for player B. So for player B, you work on the similar lines. Just like I have worked for player A, exactly on the similar lines you work for player B. You define the decision variables for player B. The variables are this time probabilities y1, y2, yn, because player B has n strategies. And we know that player B always tries to do the opposite. Instead of maximizing his minimum payoff, just like player A, the player B is going to minimize his maximum losses. So the objective function for player A, it was maximize at equals to V. For player B, it is minimize. Subjected to V minus, see, I have not explained the steps in detail, but if you have understood how we have reached the LPP formulation of player A, very easily you can figure out that this is going to be the LPP formulation of player B. So V minus, this time it's Aij into Yj. So this is like 1, 1, Y1, 1, 2, Y2. So you remember the matrix entries. So it's A1, 1, and this is A1, 2. So you know this is how they are multiplied. A11 into Y1 are the probabilities, A12 into Y2, and so on. And then you add all of them. So they are your maximum payoffs. So V is obviously always less than equal to, greater than equal to that, because the sense is opposite here. So instead of less than equals to 0 this time, player B will have a greater than equals to 0. And that's the default constraint for probabilities of strategies of B also. Some of them should be equal to 1. These strategies are non-negative. These probabilities are non-negative. And due to same reason, B is unrestricted. So this also you need not remember. You can, I'll tell you in the example that what to do. If you have already formulated a linear programming formulation of player A, then how to do the linear programming formulation of player B. Otherwise, this is also not difficult to remember, because you need to do the same steps otherwise in every example. So that's it about, I have told you LPP formulation of both the players, but there is a result which tells you, that's a theorem, but we are not going to prove it. So I'm just going to tell you the result, that LPP of player B is actually the dual of the LPP of player A. So this was the thing I was talking about in the beginning, that why it would be sufficient to just formulate one LPP. You choose always player A, give its LPP, get its structure, and then you just say, okay, the LPP of player B is nothing but the dual of this. So everybody knows how to write the dual of a given LPP. So the things get simplified there, that if you know how to write the dual, so you already have one LPP, you can easily write the other LPP. So you have two LPPs in front of you just by writing down the one LPP. So it's better you just remember the technique of one of the LPPs for player A, and for B you can simply write the dual of it. If you look at this structure, it may not appeal to you very directly, okay, how this is going to be the dual of this. But you know, there are many ways of writing the dual, and sometimes we have to do a little arrangements and redefining of the variables, but this is equivalent to the dual of that. And now let's do this thing for the example. So you are given a 3x3 game and we want to solve this. So first thing is you check saddle point will not exist. So this is the row minimum, -3. Don't forget to do this step first. This is the minimum, -2. This is the minimum, -6. So out of row minimas, the maximum is this. So this is your maximum. And column maxima, if you find 3, 4, and 2, and the minimum of them is this 2. So this is minimax. So maximum is -2, minimax is 2. Clearly they are not equal, so saddle point does not exist. And one more point I think I forgot to include in the previous lectures, that okay, whenever this maximum and minimax are not equal, but you do have some information about the value of the game. That your value of the game, your final value, which will be your ultimate answer when you solve the question completely, will actually lies between these two values. Your value of the game is always lying to lie between the maximum and the minimax. So that's why this is just an additional information, because we don't need to use this information anywhere, because the value of game turns out to be itself some number, but you can verify this, that this relationship is always going to be satisfied. Okay, so since saddle point does not exist, so I'll declare there is no pure strategy solution. So I need to solve it with the mixed strategy solution I need to find. And since it is a 3x3 game, so we cannot solve it graphically. So the only way we can solve it using the LPP formulation. So let's begin to formulate the LPP for this game. So first I'll formulate for player A, and then we'll formulate for player B. So this is one way. This is the same thing which I just wrote few slides back, LPP formulation of player A. So directly you can write it here. Like this was the structure there, and you know what is M and what is N now. M and N both are equals to 3. So M and N will be replaced by 3. So you can see this will be the structure. J equals to 1, 2, 3, I is running from 1 to 3, and this is x1 plus x2 plus x3 equals to 1. All xi is known negative, we understand. So this is the LPP. But this is in general form where we are using the notation Aij. But now you know Aijs are specifically given to you. So we just need to substitute the values of Aijs here in this. So that will give us the LPP. Otherwise, if you don't want to start like this, you directly want to work out the LPP from the beginning. So you just need to remember that, okay, the objective function of player A is always maximize z equals to v, and the constraint is always of this type, v minus this less than equals to 0. So it's easy to work out. Let me write x1, x2, and x3 here. So the constraints will be v minus 3x1 minus 2x2 minus 5x3. But since there is a negative sign in front of it, so the signs will get changed. So it's minus 3 plus 2 plus 5, because these were negative. So outside the bracket we have a minus sign. So therefore it will be, the signs will be changed. So v minus 3 plus 2 plus 5, obviously respectively multiplied with x1, x2 and x3, less than equals to 0. Right hand side we have 0, and the constraints in this LPP are less than equal to 10. And now you go to second constraint. So it's v plus x1 minus 4x2 plus 6x3. So just whatever sign is here, do the opposite, right in front v and less than equals to 0. And the third constraint is v plus 3x1 plus x2 minus 2x3 less than equals to 0. So there will be three constraints because you have three columns, and this is the default constraint. You should write that the sum of all three variables x1 plus x2 plus x3 should be 1. All of them are non-negative and b is unrestricted. So now this LPP is complete. This LPP formulation is complete. So if somebody asks you to solve it, obviously, because whenever the question is asked that solve the game, so we know that graphically हम solve नहीं कर पाएंगे, तो हमें इस LPP को ही क्या करना है, solve करना है. So at this point, it is just about how you solve it. So whichever method is applicable, because you can see the number of variables. जब आप standard form में convert करोगे, v is unrestricted, so v के भी दो variables, we will give rise to two variables. That v is some difference of two non-negative variables, v dash and v double dash. So one variable will increase from there, and then three constraints are less than equal to type. So three of them will have three slack variables, and then the last constraint is equality type. Identity नहीं बनेगी, तो obviously आपको इसमें artificial variable add करना पड़ेगा. So you can see the number of variables going up to. So it's already 4 plus 1 5 plus 3 8 plus 1 9. 9 variables you will be dealing with, and this is the smallest possible smallest possible game size which I could start with, 3 cross 3, because if it would have been 3 cross 2 वो graphically solve हो जाता, 2 cross 3 वो भी graphically solve हो जाता. So 3 cross 3 is the smallest LPP, smallest game size which needs to be solved with LPP formulation. So that's the only difficulty with this method, that the LPP which we get requires much longer calculation, because the number of variables is very, very large. Because there is no escaping from this step onwards, you have to solve it using simplex method, right? So after this, you can solve it and verify your answer. I have not solved it, otherwise I would have given you the answer, but you try this and verify your answer. This is one of the question of the book, or otherwise I'll share the answers with you when we'll be discussing doubts on this topic. And then you have to write LPP for player B. So player B, one of the ways to write LPP for player B is that you write a dual of this. क्योंकि आप ये लिख ही चुके हो, अब आपको इसका dual लिखना है. And other way is simply, which I explained, that directly just the way we have formulated for player A, in a similar way you can formulate for player B. So player B objective is always minimize. So W is the notation because dual है वो, equals to B subject to. So यहाँ पे भी constraint का structure वही है, V minus, so it's 3y1, ये minus है तो ये plus हो जाएगा, plus 1 times y2 plus 3 times y3. So that's the first constraint left hand side, and it is greater than equals to 0. Player A में वो less than equals to 0 है, player B में ये greater than equals to 0. And similarly the rest two constraints can be written, and y1 plus y2 plus y3 equals to 1, and this. So if you are asked in the question that write the LPP formulation of both the players, then you need to write. But say if the question is just about solve the LPP, solve the game, then no need to write two LPP formulations, because you just write the LPP formulation for player A, solve this linear programming problem, and you know that in the optimal table you will get the solution of you will get the values of x1 x2 x3 original decision variables, means ultimately you will get the solution of this particular LPP. And now our ultimate aim will be, finally we will be left with to find the values of y1 y2 and y3. So all of you know how to read the solution of the dual from the optimal table of primal. So it's sufficient to solve just this LPP. From its optimal table, you can read the optimal solution of the dual. So no need to write the formulation for player B. So it really depends upon what particular question is asked. However,